Now that the conference is officially open, I have the pleasure to introduce to you our first keynote speaker, Philippe Ciais, from the Laboratoire des Sciences du Climat et de l'Environnement in Paris. Philippe Ciais got his master degree from the École Nationale Supérieure de Paris in 1989, his PhD in University Paris-Saclay, working on the isotope records from Antarctic ice cores to study the climate of the last 15,000 years. Then he moved on to a postdoc at the National Oceanic and Atmospheric Administration in the US, working there again on isotopes, but this time on carbon and oxygen isotopes to monitor the flux of carbon dioxide in the atmosphere. Since 1994, Philippe is with the Laboratoire des Sciences du Climat et de l'Environnement, and he is now Associate Director of the laboratory, responsible of more than 300 staff. And Philippe is really a pioneer and very well recognized scientist in his field. So the global carbon cycle, its interaction with terrestrial ecosystems and also climate change is the most cited scientist actually in this field. And we are very proud to have Philippe with us here today for this opening keynote lecture. So Philippe, the floor is yours.
Okay, good morning. Thank you for the invitation. I'm very happy to give this presentation on the use of many satellite and ground-based data to better monitor ongoing changes over forest at the scale going from tree to globe. The increase of carbon dioxide in the atmosphere is the main driving force of climate change. CO2 has already risen up by 50% now, above pre-industrial levels. The increase is due to human activities, mainly today the burning of fossil fuels. But we are lucky in the sense that our planet has a global carbon cycle, and the land and the ocean are absorbing about 50% of man-made emission on average each year. In this context, forests play a particularly important role because forests currently absorb about a quarter of human emissions at the global scale. They are also central to the European neutrality objectives. As you know, Europe has increased its ambition to bring emissions 55% below the 1990 baseline, but this time using the land use sector. And in the land use sector, we are mainly talking about the largest carbon sink, which is in European forest. More precisely, the European member states have agreed upon to maintain a land use sink of about 300 million tons of CO2 per year in 2030. And yet forests are vulnerable to human intervention, logging, and also to climate change, fires, windthrown, and different sort of disturbances. This happens globally, but it is also affecting us in Europe. Today, forests in Europe are a significant carbon sink. They grow more than what they release as carbon dioxide. And the reason why forests are a large carbon sink is because they are relatively young. After World War II, many forests in Western and Central Europe were clear-cut, and since then they have been replanted. There have been large national programs of forest restoration, forest plantation. Forest area is slightly increasing at the European scale. So this regrowth of forest over the past 80 years is the main reason why we have a carbon sink in Europe today. It's mainly demography. However, at the same time, European forests have continued to provide many important services. Forests are important for maintaining precipitation clouds, purifying water, hosting diversity, but but also for providing wood to the economy. Wood is used for energy, for materials, and so on. And at the same time, then forests have been growing more than the amount of carbon that was harvested from them. They have continued to provide a significant amount of wood for the economy, creating jobs, etc. However, when we think about deforestation, we always think about Indonesia, Brazil, but we do face recently the fact that there are a lot of old carbon-rich forests in some regions of Eastern Europe, and some of these forests are in fact exposed to cutting, logging, and when you take a biomass-rich forest that has more than 100 years old and replace it by young trees, of course, you will have a strong loss of the carbon sink capacity. In addition to that, climate change is unfortunately processing, just as the IPCC has predicted it. And we are finding out that Europe is one of the most vulnerable regions in terms of recurring drought and heat waves in summer. We all have the reminders of the extreme drought of 2003, was an event that was supposed to return every 100 or 150 years, but now we have another extreme drought in 2010, droughts in 2018, in particular in Central Europe and southern Scandinavia, that affected forests in different ways, with large amount of wildfires. And more recently, it's not on my graphic though, we have strong droughts in France, for instance, in 2022, and heat waves up until the recent years. So drought have become almost the norm, and even for a global warming of 1.5 degrees, it's projected that they will increase in frequency by a factor of 3 to 4. So they clearly pose a threat to the integrity, the carbon function of forest and also other ecosystems in Europe. So you may claim that European forests are on the brink of change. Of course, very long-term perspectives are best given by ground surveys. You can see in this graphic, which is not completely updated, we now have ground observations for the last decade, that it seems that the exposure of forest as a whole to a number of climate-related disturbances is increasing over time. In terms of intensity, it's really storms, windstorms, that increase mortality by more than 500 to 600% when they happen. They are very severe, but fortunately rather rare. Droughts are more frequent, and they can cause the dieback of forests, but droughts are also worrisome because they weaken the ability of trees to defend themselves against pathogens and insects, and we now have in Central Europe, in Germany, in Belgium, in France as well, a very strong outbreak of bark beetles. Bark beetles were something from Canada, You look at the newspaper, they were destroying forests in North America. It was far away from Europe. And now, because of trees having been weakened by the dry conditions of 2018, we see an explosion of those insects that create a serious problem for conifer forests. So tree mortality is observed to have dramatically increased over the last decades. Typically in France, for instance, for the National Forest Inventory, we see that tree mortality has increased by 50%. This is enormous. What is even more worrisome is that new forest plantations are failing more than before. In France, we have a 38% failure rate of new forest plantation, which means that you plant a new forest, it may not be adapted to the changing climate, and the trees are dying back. So this makes it all extremely challenging, I believe, for the EU to meet its commitment of sustaining a carbon sink in the land use and forest sector. And unfortunately, we may not have today the data we need to seamlessly monitor carbon changes in forest. This is a graphic from my colleague Giacomo Grassi in GRC. He showed on the right the kind of expected target sink, which was quite reasonable because it was set based on, observed forest carbon sink back in 2015, and it seemed quite reasonable at the time to be able to sustain in 7 years from now, by 2030, for the Paris Agreement, a carbon sink of about 300 million tons CO2 in the forest sector. But as you can see, all over Europe, this is an average for all the European countries, in the forest land, there has been quite a significant decline of the carbon absorption capacity. It's about 15% of European scale. In France, it's 40%. So we are not sure now if we will be able to meet this agreed upon European target. And I think that's a very, very serious concern for the Commission and the Member States. So what to expect? Exposure to climate risk has increased. To some extent, there are a lot of debates about should we cut the forest more and manage them more intensively to substitute, for instance, wood products for more carbon-intensive goods like concrete or steel, or should we give the forest a break and let them regenerate, regrow, and store carbon? Of course, if you let forests grow, they may be also exposed to disturbances. We know that all forests hold the largest carbon stocks, but they're also vulnerable to climate. And when we replace an old forest, which is rich in carbon and biomass plantation, it will be a long time before we reach again carbon neutrality. So it's clear now that in the face of climate change, we should manage wisely our forest, like a sequestration portfolio. And the question is, do we have the information to make such a well-informed decision? Because decision-making is done, by landowners, by regional governments. In France, we have 3 million of forest owners, and we have 100,000 farmers, which means that the forest ownership is extremely fragmented, and it's very difficult to design policy to appropriately manage all those forests which are owned by a lot of people that have very different interests. Currently, the main asset for knowing about forests are called forest natural inventories. They have not been invented for monitoring carbon resources. They have been established by countries more than a century ago to monitor wood resources, what to expect in terms of wood extraction, and they have proven good enough, following the Kyoto Protocol, to provide national-scale carbon stock assessment. However, forest inventories consist in sampling very local plots, less than 1 hectare. Typically in France, we have about 7,000 new plots, which are measured every year. But this is clearly not dense enough to capture all the heterogeneity of forest, given the scale of disturbances. And forest inventory will only give you a change at a specific location over a 5-year average. This is a real problem. Imagine you have a climate shock, for instance. You lose 20% of your biomass because of the climate disaster. You will only see revealed the amount of loss maybe 4 or 5 years after the event has happened. And this is really a problem for our commitments to climate treaty. We also have a number of scientific networks, in particular the ICOS networks of flux towers in Europe. This is extremely good for understanding, the micrometeorology and the climate impact on carbon fluxes. But these data are still a bit what you would call acupuncture, a few points, very precise, rather expensive research measurements. But none of these current measurements provide a continuous wall-to-wall estimates of where carbon is stored and where carbon is potentially lost. That's, of course, why satellites are so useful, because they provide continuous mapping. However, there is a trade-off. If you want long time series to look at changes behind you, you have to rely on classical sensors, such as MODIS, for instance. MODIS has a good revisit time, but it has a very coarse resolution. At the scale of 1 kilometer, you can sometimes not separate cropland, grassland, and forest in the same pixel of MODIS in Europe. We have Landsat, also long, but more sporadic in time. In the early time of Landsat, you have only a few images per year. We now have new microwave, radar and passive sounders. And I will make the case in the presentation for the use of high to very high resolution images. We're talking about Sentinel data at 10 meters, but also about other satellites like planet data, for instance, at 3 meters and better. So satellites open a new window to monitor wall-to-wall forest carbon for sure, but one important point is that forests are extremely heterogeneous. As I was saying, 3 million forest owners in France. The typical size of a single forest is less than 100 by 100 meters. Inside this parcel, you can have very different type of trees. And up to now, the heterogeneity of forests could not be measured across the entire continent. But now we have new tools that do provide us with both excellent time revisit and very high spatial resolution. And this is a new frontier for understanding forest management intensity and practices, forest health, disturbance, species, and age. I want to give you an example. You have to believe me, this is a MODIS image in a small corner of Senegal in Africa. What you see is big squares of colors indicating the spectral reflectance of the sensors. This is the same region seen by Landsat. You see some patterns, but you're not quite sure of what you have. And this is the same region seen with the 3-meter images, and you clearly discover, what is on the ground. You have a river, you have some shrubs and some fields, agroforestry, and so on. Another example here, it's a place in Germany. You didn't guess it from MODIS. Seen from Landsat, again, you have some structures, but you don't really know what it is. And with a 3-meter image, here it's a planet image, for instance, you see there is a motorway crossroad, there is a plantation. You can distinguish different type of trees by their different reflectance. You have big trees here planted, and so on and so forth. So clearly, high resolution reveals the heterogeneity of carbon across forest, but we have some drawback. First of all, if someone gives me the recipe of a satellite that measures carbon, I would buy it, but we just have indirect measurements. We have optical measurements of the color. We have LiDAR measurements related to the forest backscatter, the forest structure, the volume and height of the forest. We now have some LiDAR measurements. So it's clear that if we want to develop a forest carbon monitoring system, we need to make an intelligent fusion of different sensors. There is no sensor that will be, this is the carbon sensor for forest. Although, efforts are being done, of course. Secondly, satellite data still need to be evaluated and calibrated using ground-based observation. It's always the same story. Like for the weather forecast, in the beginning, weather stations are good. Now we know that the weather forecast is, in fact, better from satellites, like in the southern hemisphere, than from the sparse ground-based network. I would bet you that if I have to give this presentation 10 days from now, probably I would be much less insistent on the reliance of ground-based data, but today we are in the transition, and ground-based data from inventories are still extremely important. There is, of course, a huge challenge that was mentioned by previous speakers. It's a real deluge of data that we have to be able to process. And I would argue that one way to make sense of this data is to move from using physically based retrieval models, like we've been doing for more than 2 decades, but to use the power of deep learning and artificial intelligence. Typically, the situation looks like that. You have big set of data, very different in terms of structure. You have sparse forest inventory data. You have, for instance, the planet images. They are incredible, daily data, 3 meters, but the spectral purity is very bad. You just have an RGB image and an infrared band, and that's it. You have much better spectral data and higher quality data from Sentinel-2, Sentinel-1. You have now some new measurements from spaceborne LiDARs, in particular the JEDI measurements that gives you the first ever footprints of forest height and structure. And we want to have maps. We want to have typically annual forest cover map. It's not that easy to have a very accurate tree cover map. I will show it later in my presentation. We want to have annual carbon maps to be able to monitor changes, even monthly detection, because sometimes extreme events happen in a few days and months, and you want to have an idea of what's going on, and to relate the carbon map to what is going on in terms of activity data, whether activity are wind-thrown, fires, insect attacks, and so on. So in order to reach that, it is possible to train models, deep learning models typically, in order to produce the desired quantity, but of course, all the products you will generate have to be carefully evaluated using independent data. Independent data can be a subset of the satellite data you don't use for the training, or it can be a completely independent measurements like ground-based measurements. So in the following, I will give you a few examples of work we did in collaboration with colleagues from University of Copenhagen, Department of Machine Learning Science in Münster, INRA, and also JPL in the US. We have been trying to produce new maps of forest risk, forest types, forest carbon, by using deep learning, a lot of GPU computing power, applied to a different set of satellite image. And I would like to walk you through different examples. The first one is that we produced one of the first maps of global forest biomass change over the last decade. We are doing high-resolution maps, talking about a few tens of meter resolution for biomass and height. Digital map of tree cover at 3 meters over continents, and also digital maps of forest carbon at an unprecedentedly high resolution. First example, it's an interesting story because we've been using the SMOS satellite, and SMOS is a European ESA satellite. The purpose of SMOS was to measure soil moisture and salinity. And people who are retrieving soil moisture, they're annoyed because the vegetation contains some water, and it prevents them from having a very good retrieval of soil moisture. And in fact, if you know the water content of the vegetation, you can separate it from the soil moisture emissivity signal. The water content of the vegetation is related to the volume and therefore to the biomass, and that's what we did using a model applied to the SMOS data. We were able to transform what we call the vegetation optical depth data retrieved from SMOS, now combined with SMAP, at a coarse resolution, but it's a global map. And this allowed us to produce, in combination with the ESA CCI biomass map, the first map of annual biomass change that reveals interesting patterns. In green, you have the largest forest carbon sink area in this region of southern Russia, where there have been a lot of agricultural abandonment, northern Siberia, in southern China also, where there is a lot of plantations. But you can also see carbon losses associated, for instance, to fires in Australia in 2019, and to ongoing deforestation in the Congo Basin, but also in the southeast part of Brazil. If you compare this map of biomass change in forest with the map of just forest area loss that we get from Landsat, there is quite a good correspondence in the tropics, and there is indeed an emerging relation between the forest area loss and the biomass loss. Although in some regions here, like in Louisiana and Southeast US, you have a big forest area loss, but there is no carbon loss. This is because this is intensively managed forest. So you always have clear cut, you see loss, but of course, the forests are permanently regrowing, and overall, they don't show a pattern of carbon loss. Moving now to high resolution, we have been facing the problem that radar is radar, optical is optical, none of them is carbon. And on the other hand, you have this brand new mission called JEDI, which measures forest height. Height is a prerequisite for biomass, of course. But unfortunately, JEDI only has point. JEDI doesn't provide you a map, otherwise the problem would be solved. So what we did is that we used a high-resolution map from Sentinel-1 multispectral, Sentinel-1, Sentinel-2 multispectral, and the sparse JEDI spots of forest height to provide a continuous, seamless map of height at 10-meter resolution and biomass. This is an example. You have a Google Earth image. You have basically the result of our model. And this is a map for France at 10-meter resolution. This is a small forest called the Ciais forest in the north of France. This is just a Google Earth image. You see the JEDI measurements, they are very sparse. You see some structures, some forests are tall, some forests are short, but it's very hard to say. After you apply the kind of deep learning fusion of the Sentinel and the JEDI data, you really reveal the entire structure of the forest with plots that have been harvesting, young forests growing, and some forests that have biomass, even some kind of gaps and things like that inside. When we validated this data using independent information, we get a very good result. This is typically the mean absolute error compared to the completely independent annual forest inventory data is on the order of 3 meters, which is really good. Out of that, you can also derive what you call forest recovery curve, because you know the biomass today for each pixel, and you know the previous disturbance from Landsat. So for each region, you can create a kind of biomass or height versus age curve. And this is very important because those curves can be used to manage forest. Basically, it gives you the expected amount of carbon that you will get after 10 years, 20 years, 40 years, etc. And using high resolution and crossing that with a map of species, we can have those kind of sequestration curves for each type of species in every region. We can also apply very high-resolution biomass data to understand better the losses. This is what happened in France in 2022. It's an extreme fire year. And normally in France, fires are prevailing in the Mediterranean region, and there are some extreme years. But in 22, fires happened into new forest. They happened in this Leland plantation and also in temperate regions in Brittany, in Jura. And we found out that although the burnt area was quite high in the Leland forest and relatively low in this new temperate forest that were never burning before, we found out that the total amount of biomass affected was still high in the temperate region because they are much more carbon rich. The carbon density is much higher than in the Mediterranean area. We also applied the model to look at changes, and we were quite surprised to see that we can monitor over time using the same kind of deep learning model. Carbon loss, all the red areas are forests that have been clear-cut, but also carbon gains. And carbon gains are quite difficult to capture because forests, of course, when they lose carbon, you have a big signal. You go from 30 meters to 0 height. The height increment over a year or two is less than 1 meter, and the model is still good enough to detect the forest growth signal over time. We also tried to apply this model to the tropical forest. It's much more challenging because they are very tall, they have very complex structure, and we found out that here in the Congo Basin, for instance, we had a very good agreement between our reconstruction of forest height and completely independent airborne LiDAR measurements. Now, another example, we used this time the planet data, and we trained the planet to do a tree cover product at 3 meters and a tree height product at 3 meters by training them against airborne LiDAR measurements. So we trained the model at a few locations where we have airborne LiDAR, And we produced the first 3-meter height map of Europe. It looks like this. This is a kind of planet image. This is the true airborne LiDAR height, and this is the reconstructed height. And we learn interesting things, is that in Europe, you have a lot of trees outside forest, in particular across the Atlantic regions and the UK, Netherlands, and Denmark. More than 20% of the tree cover is not in the forest inventory because it is not forest. It is urban trees, gardens, roadside, hedgerows, and so on. And still, they sum up together to about 60 million hectares. And you have land cover classes like grassland and croplands, where you have trees, but they are not detected as such. We applied the same method for Africa to produce a tree cover map of entire Africa with a lot of trees outside forest in dry regions. We have counted 11 billion trees in the Sahel regions using very high-resolution imagery in this paper published in Nature. We have counted all the trees of Rwanda, and this model is used by the government of Rwanda, this time not using satellite, but using airborne images. And we can also see changes in the number of trees in the space of 10 years. This was a degraded forest, and you can see the appearance and the growth of individual trees. For this, we use a segmentation model to segment all the trees of the entire country. And last but not least, we also sampled all the trees of India over the last 10 years. India is the biggest agroforestry country in the world, and we found that a lot of large agroforestry trees have disappeared, more than 36 million of them, in particular in the center of India. So all the pink dots correspond to big trees that have disappeared. So in conclusion, we need an integrated forest monitoring system. Satellite observations today, I would say that they are as good as the effort invested in calibrating the instruments and validating the product. So it's clear that there is an emergence of big data. Artificial intelligence is helping us a lot to do things that physical models or simple regressions would not be able to do. But we still need ground data to secure the quality of the data. We have a deluge of satellite data from different sensors. This is a clear challenge. It's a limitation for previous, like, physics-based algorithm. Recent advances in deep learning allow us to monitor forest carbon, forest management, forest species, forest health, with an unprecedented resolution in space, time, and accuracy, hopefully. Tree-level analysis is now made possible. It's very important because when you have mortality, it's only a few % of the trees which are dying. It's important to know that at tree level. And last but not least, ground-based data still remains a critical asset for the evaluation of satellite-elaborated product. So with that, I would like to thank you for your attention. Take any question if you have.
Thank you very much, Philippe. For this very enlightening talk, I'm sure there are many questions from the audience, so please don't be shy. The floor is yours in the audience now for questions.
Hello. So my name is Martin Stepanek. I'm from Austrian newspaper Der Standard. And I wonder, like, from the models you trained, were there any big surprises when you compare them to existing models or existing assumptions? That's one question. And the other one is maybe with the single standing trees outside the forests. I mean, what is sort of the relevance of it for decision making, or is there something you found out?
Yeah. Well, the maps we have been producing have no equivalent, so it's pretty hard to, they look obviously better when you compare them against ground-based measurements, but still they have some issues. Typically, all these deep learning models have problems to capture the tails of the distribution. So if you have only very few very tall trees that are 40 meters high in a few stands of Austria, the model will be trained by, a lot of data from other forests, and it still has a tendency to underestimate tall forest height. Secondly, to go from height to biomass is tricky because, like humans, after some age, the trees don't grow taller, but they grow fatter, right? They grow in thickness. And of course, JEDI is measuring height, it's measuring structure, but it's more difficult for old forests to essentially have a good transfer function between height and biomass. As for trees outside forest, well, those trees provide a number of services. For instance, hedgerows are retaining soil for erosion in many regions. They're also providing host for biodiversity. In cities, urban trees are providing cooling services during heat waves and so on and so forth. So right now, they have not been on the carbon radar, and I believe it's important to monitor them because we give, for instance, subsidies to farmers for planting hedgerows, but if they plant an hedgerow and then 3 years after they got the money and they cut the row of trees, you will not have carbon or trees on the ground. So I believe it's still important to cover those trees, especially because in some countries like Denmark and UK, they represent 30% of the total tree cover. So it's definitely quite important.
Hello, Miriam Gonzalez from Op42 here. I'm curious about the commercial data used for the project. I see that only planet data. Is there any other interest for using more sources right now that we have so many options and also more people, more companies coming in the new space sector?
Yeah. Planet, of course, they have a good offer because they cover the globe, and for academics, they give you a good license. The problem is that if you are a company or a government, when I pay $50,000, you will pay $5 million to access the Planet data, and they have also some restriction in the product you derive from the Planet data in terms of derivative and derivative of derivative. So personally, I think it's much better to try to use publicly available data. Planet is 3 meters, spectral quality is not so good, but Sentinel is 10 meters, but you can have a super resolution with Sentinel. We could go down to 5 meters using the slight difference in the orbit of the different instrument. So I believe that the future is really more on the use and the exploitation of publicly available data. And of course, new space data for imagery is always welcome. And we have also some data like spot data and so on are still very important for past analysis. But personally, we use a lot the Planet data, but I would think that there is a lot to be done with the Sentinel images.
Thank you.
Thanks a lot for the talk. You said you're annoyed by the tails of the distributions with DL. Are you able to characterize that? Do you know the bias? Do you have an estimation? Are you overestimating or underestimating?
No, typically, depending on the loss function you give to these deep learning models, the models are lazy and they try to go to the mean, unless you have a preferred weight to some tails of the distribution. So, okay, I don't have my slides here, but typically for the case of the forest in France, but also in Ghana, tall trees are less than 1% of the total area. So you have to oversample this data, basically, in order to train the model properly to be able to ask them to capture the tall tree structure. On the other hand, models have also problem to capture the height of the small trees because JEDI is not very good with the ground return uncertainty at capturing small trees or shrubs, but I would think this is less of a problem for carbon monitoring if you have an error of 2 meters between crops and small shrubs. It's definitely a challenge for tropical forests because you have very, very tall trees, sometimes 60 meters, and there is sometimes no ground return from the JEDI data. Well, we were quite happy to see that our kind of vision transformer model was able to work to retrieve height for tall tropical forest when it is properly trained using the JEDI data. And in the tropics, you have also the problem that there are clouds. So all the Sentinel data, you have to create a lot of mosaics and compositing in order to get images that you can use for your deep learning models.
Thanks.
Hello, I would like also to ask about the saturation because C-band radar is not very well penetrating as well as optical data. So how come you can estimate well height of the forest in Amazonia? Yeah,
that's the magic of deep learning, is that they work. Typically, you exclude 30% of the data. You use them in blocks. You use them for cross-validation, and the model has a good performance. Because the deep learning is learning from contextual inference. Basically, you don't only have the C-band signal, which saturates, and the optical data, which saturate, but you have some kind of textural information. You have different structure in a similar forest in your entire territory. And this is information that is exploited by the deep learning model in order to, let's say, go above and beyond the saturations of the radar sensor. So we were quite surprised to see that, at least in Europe, but even in the tropics, there is enough information in the image structure, in the latent features of the image you extract from your deep learning model, to say something about height, even in forests where you should have some saturation. That's because we use optical. So optical, you have some kind of, tree patterns and texture, multispectral, optical, and also the radar data. So it's really the combination of the two that is enabling the model to do it. The problem with this deep learning is that it's a black box, They work objectively, and they work in cross-validation. You do rigorous tests. They are very good. But you still don't understand how they learn and what are the features which are important for them to extract from the images. So we are looking into that now, because sometimes it drives you crazy. You have an incredible result, and you don't completely understand what kind of information the model is picking up in order to provide this result. Of course, we have methods to better understand, but that's a drawback. If you want a diagnostic, it's good. If you want a very good understanding of the actual information exploitable by the model, it's a bit more difficult.
Yes.
Yes, thanks for this talk. Very, very interesting and inspiring. Fusing data at 3 meters globally everywhere is, of course, a challenge also in terms of co-registering these data. So what would you say is the influence of co-registration errors of all these different data sets, and how did you mitigate that? How did you correct for that?
Yeah, indeed, you need to have a good co-registration, and it is a problem for JEDI, because JEDI is on the space station and it's slightly moving, so the collocation of a JEDI footprint is today no better than 10 meters. 10 meters is the problem, because the instrument will tell you there is a 20-meter high, and then when you overlap this with the Sentinel image, there is a cropland, because you are just at the edge between a forest and a crop field, for instance. So we are producing global data set. Co-registration, of course, is very important, but we still have possibilities, again, with the deep learning technology, to correct in the loss function of the model for co-registration error. So we can have an adaptative cost function in the way we build our model that includes the location errors, in particular for the JEDI data, and that improves the performance. So we can basically include registration errors in the model when we train it and when we essentially have it match target data. So again, it's frustrating, because, you can also ask deep learning to help you with the co-registration problem. I'm not coming from artificial intelligence or deep learning. I just discovered that 5 years ago, and still quite fascinating with it. And it does things that physical models or, let's say, regressions would not do, certainly.
Okay, many thanks again, Philippe.
Thank you.
Deep learning is fascinating, but I think you will all agree that your presentation was also very fascinating, and I'm sure there will be many questions now to you during the coffee break, and maybe if you stay with us a little bit today during other period of the conference. So many thanks again.